All right, ladies and gentlemen, I am here with you guys to go back over, help you review for your AP exam. This is the next section in Unit 1, which is on mass spectroscopy of elements. And just wanted to remind you that when we look at the mass spectroscopy and what's expected of you guys on the AP exam, it's only going to be used to help you guys identify elements. You will not be asked to identify specific compounds or functional groups or anything like that. It will simply be using mass spectroscopy as a function of how we use that to determine isotopes and other quantities and values as it pertains to elements. So just want to go ahead and get that out of the way before we even got started. And so let's just go ahead and dive into what is mass spectroscopy and what does it help us to do. Now, again, we've seen this kind of a little bit of a joke. Scientists always messing with each other, right? So the poor guy, his lunch got put through a mass spec machine, and now he's got all these different readouts, and he's trying to figure out what exactly it is that he had. So, it's humorous. It's science humor. So, all right. So here is the purpose of mass spectroscopy. Okay, I'm going to pull everything up first, and then we'll just kind of go through it one by one. So a mass spectrometer, it's a device that chemists use, and what it allows them to do is it allows them to determine the elemental composition of a sample. From that, so it can tell you what specific elements make up a molecule if it's something that's really large, or if you're looking at an elemental sample, what different isotopes make that particular elemental sample up. It can give you the masses of the particles that are present. So again, looking at those isotopes, you can get the individual masses of the isotopes, or if you've got different forms of molecules that are present as well. By using mass spectrometry, you can determine potential chemical structures of a molecule by analyzing the fragments that get produced in that spectra. When you start looking at, again, compounds and molecules and large substances like that, if you have an unknown sample, you can run it through a mass spec machine. You can then compare it to known mass spectra information, and you can then match it, your unknown, to a known compound. And lastly, there, the isotopic composition of elements in a molecule. So not just simply talking about elements, but when you look at the molecule, how many isotopes are present of the different elements that make it up. Okay, so that is the purpose of mass spectrometry. Now, this should be kind of familiar to us. We should have seen something like this. We did a POGL on this at the beginning of the year. And if you remember, what happens is that you start with your particular substance, okay? And it gets ionized. And as it gets ionized, that means it's going to be losing electrons. And then it gets focused through a beam, and it goes into the mass spectrometer. Now, once it passes through that, there is a magnet that is present. And the purpose of that magnet is to attract charged particles to itself. And then as you can see, there are 3 different paths that get taken for this particular substance. Now you got this M divided by Q, that's just the mass to charge ratio. So the mass is 46 with a charge of +1, right? And so you got 46, 45, and 44. Then it passes through, amplified, and then it gives you an output. And from that output, you can figure out what are the different substances or what are the different particles that make up this substance. Now, you also should note, just even from this diagram, that your heaviest massed particles get deflected the least. Okay, that's because it's harder. It requires more force to deflect something that's heavier. And so that's why your lightest particle, the one that has a mass of 44, gets deflected the most in this particular process. Now, just a quick recap there. So the ionizer, that's going to be your ion source here, converts some of the sample that you have into individual ions. Then you've got your mass analyzers that are going to separate the ions according to their mass to charge ratio. And then the detector, that's going to record either the charge induced or the current produced when an ion passes by or hits its surface. Now, obviously, the higher the charge or the higher the current that gets produced, then the bigger the readout is going to be, right? So obviously, if that current is higher, it means that that particular quantity or that particular particle is occurring much more frequently, which lets us know, okay, it's more likely to occur in this particular state as opposed to another. And we'll analyze that a little bit more, but hopefully that should make sense to us. Now, these are just a list of different mass spectrometry methods, and it gives you the different mass ranges for which it's useful for. The AP exam isn't going to ask you anything specific about any of these types, but it's just good to know for your own reference how these different forms of mass spectrometry can be used. This will be invaluable to you if you go to take any college level chemistry, even organic. You will get to use a mass spectrometer, and so it'll be interesting just so that you can kind of have an idea of what mass ranges and what type of substances are best fit for the different type of mass spectrometry you're dealing with, okay? So that gives you an idea. You got electron impact for your relatively small substances, chemical ionization, again, for your relatively small substances. You've got electrospray. This is going to be good for like biological, like proteins, peptides, DNA, things like that. You got fast atom bombardment. As you can see, handles a little bit larger particles than our electron impact and chemical ionization. And then you got your MALDI, matrix-assisted laser desorption. Again, for your nucleotides, your proteins, and your peptides. This deals with very massive particles that we're dealing with here. Now here, this is a sample readout of a mass spectrum of, this is a very simple molecule, carbon dioxide. Now again, keep in mind the AP exam is not going to ask you guys to break down molecules. It's only going to ask you to break down elements, okay? And what we should notice is that we've got 1, 2, 3, 4, 5, 6. There are 7 peaks that are here, okay? But what we should be able to do is we should be able to identify what each of those peaks corresponds to, right? So this largest peak, we're dealing with carbon dioxide. So the molecular ion peak is this one right here. You take carbon-12, combine it with 2 oxygen-16s, and that gives you a mass of 44 with a charge of +1. So this is the thing that, in terms of its intensity, this is the thing that's being produced the most, right? Now you've got these other fragment peaks that come before the molecular ion. This would be a fragment at 28. That's a combination of just carbon and oxygen. Here you've got the oxygen-16 peak. And then here you've got the carbon-12 peak, right? And so again, we really focus in on the ones that are kind of producing these higher relative intensities, okay? Now, here's an element, bromine. Now, bromine's unique. It does exist as a molecule, Br2. This is going to be something more like of what the AP exam is going to ask you guys to look at. They might give you a spectrum, and they ask you to figure out what are the different isotopes, what's the abundances, things like that. So in this particular case, they tell us that bromine has 2 isotopes. One's at 50.69% and the other's at 49.31%. And so if you were asked to label this particular diagram, I would anticipate that you guys should be able to do that. Okay. Now, they tell us the mass numbers of bromine here, 79 and 81. That's going to match up with our mass to charge ratios, okay? So if we're starting over here at our smaller peaks, this first one right here, that's going to correspond to our bromine 79. And then the one that's beside it, that's next largest, that's going to correspond to our bromine 81. Now the question might be, what exactly are we dealing with over here at the far right? So let's break that down a little bit. So these far right peaks, those are your molecular ions. So this is going to be the Br2 plus ions, but notice that they come in, I guess in a sense, 3 different varieties. So the first one is a mixture between bromine 79 combining with bromine 81. That's your highest relative intensity peak. Then on the other hand, the one that's to the left is going to be that combination of 2 bromine 79s that have been combined and then have a +1 charge. And then our third peak over there is our bromine 8181. Now again, it should make sense that our bromine 79 peak is a little bit larger than our bromine 81 peak because that bromine 79 occurs much more frequently. Well, I'm not going to say much more, a little bit more frequently than our bromine 81, right? And then our fragments, our element fragments, we've got our bromine 81, which is here, and our bromine 79, which is here. All right. Hopefully this is making sense to you guys. Now, again, the AP exam is not going to ask you guys to break down larger molecules, but if you do get the opportunity to work with organic chemistry, you might see mass spectra that look like this. And so, obviously, the larger the molecule, the more complex the spectra. But then you can use that information to help kind of break it apart into chunks and then eventually ultimately identify different functional groups. And then maybe you'd even be able to compare it to a known spectra, and you'd be able to identify this is actually codeine C18H21NO3. Now, mass spectrometry, in terms of applications, obviously more than just simply chemists use mass spectrometry to identify isotopes, has a practical application in the area of forensics. So it can help forensic chemists to identify unknowns such as illegal drugs or identify powders or substances that have been left behind at the scene. Now, most of the time when forensics scientists collect samples, they're not pure, and so they got to be separated from a mixture that's being formed. And so what gas chromatography, that's something that allows chemists to separate those components of the mixture, right? So then you get these different readouts so you can break it apart. Now, mass spectrometry gives fingerprints. These are the components so that they can be matched with existing known spectra, right? And so let's say you've got your unknown that was left behind. It's a mixture, you know, it's a conglomeration of a lot of different things. So you place it through gas chromatography. It separates out your components. So then instead of having just your rectangle, your star, your circle, and your oval, you get each of those components individually. And then from there, you can pass each of those individual components through a mass spectrometer, and then you can get your readout and identify what are the different substances that are present. You know, here's our rectangle, here's our star, here's our circle, here's our oval. And then from that mass spectrometer reading of the rectangle, the star, the circle, and the oval, you can then match that up with something that's already known. Pretty useful. Now again, from the AP perspective, mass spectrometry helps us best understand isotopes and how chemists have been able to identify what different isotopes of an element exist and how we know that this isotope occurs most commonly. So we know from our understanding of honors chemistry that atoms that have the same Z, that atomic number, the same number of protons, but a different mass number, A. Remember, if you have a different mass number, that just means that it has a different number of neutrons. Then what that tells us is that we have these different isotopes that exist of that element. Now, naturally, elements have isotopes and they occur in nature in precise proportions, right? So not all of them are always one specific isotope. There is a ratio of these different isotopes that make up the element that occur in nature, right? And so for the chemist, it's really important to be able to figure out what exactly are those fractional abundances or those natural occurrences, like how often does it occur in nature? If we can figure that out, then we can get an idea of what the masses, like that are on the periodic table, how we can get those accurately. Now that leads us into our conversation about atomic weights. The average atomic mass, that's that decimal number that's on the periodic table, is the average masses of all the isotopes of that particular element. So it takes into account all the different isotopes of that element that exist and the abundances of those isotopes. So for example, let's say that we determined that carbon has 2 naturally occurring isotopes. Now we know that carbon has more than that, but based on this example, you've got 98.892%, that's carbon-12, and 1.108%, that's carbon-13. So the average mass of carbon then would be a function of those abundances and the masses of each of those isotopes. So taking that into consideration, we would take that percentage, 0.98892, multiply it by the mass of the atom, which in this case is 12 AMU, from the 6 protons and 6 neutrons that carbon-12 has, plus we're going to multiply it by the percentage of the carbon-13, so that 0.0108, times the mass of carbon-13, which would be 13.00335. We could just say that that's 13. And that's where we get this number 12.011 AMU. And if you look on the periodic table, that's the average mass of carbon. Now, for chemists, you will see that atomic weight can be interchangeably used with average atomic mass. You're probably most likely going to see average atomic mass more likely than atomic weight, but just know that if you see that term, it's asking you for the average atomic mass. Now, these atomic weights, those are listed on the periodic table. So when you look at your periodic table, that's that decimal number that's directly below the element symbol. And that can be useful to us when we start doing stoichiometry and other calculations as well. All right, so with that, that wraps up our discussion of mass spectroscopy. So go ahead. We've already done these questions. If you need to look back at them, look at them. Come and talk to me in office hours if you're stuck on something. Thank you guys for stopping by, and look forward to seeing you guys again.